everyone. In this video, I would like to talk a little bit about the mean value theorem, a very important theorem in calculus. So what I'd like to do is take a look at the theorem, we'll read through it, we'll make sense of it, we'll put a diagram to go along with it so we can make sense of it even further. And then after we do that, we'll put it to use in a specific example. So let's just start by reading through what the mean value theorem says. It starts with, let f be a function defined on a closed interval from a to b. If f is continuous on this interval from a to b, and if f is differentiable on the open interval from a to b, then there is at least one number c in the open interval from a to b for which f prime of c is equal to f of b minus f of a all over b minus a. So we have a lot going on here, and what I'd like to do is just go back to the beginning of the theorem. We'll go through step by step, and we'll make sense of what each part says. So back in the beginning, let f be a function defined on a closed interval from a to b. So we have two endpoints. We have one at a and we have one at b. And our function is going to go between these 2 points, and a and b are going to be the endpoints. It's a closed interval, so those are going to be included. F is continuous on this interval, so there are going to be no breaks. And f is differentiable on the open interval from a to b. Remember, we can't take the derivative at an endpoint, but everywhere in between, this is going to be differentiable, so there are going to be no sharp corners, there could be no cusps or anything like that. And then as long as those two conditions are met, then we know there's going to be at least one number c, somewhere in between a and b, for which f prime of c, the derivative at c, is going to be equal to this expression. Now this expression should look familiar. F of b minus f of a all over b minus a. This is the slope of the secant line that connects a and b. So f of b, this is a y value. F of a is a y value. These are two x values. So this fraction, this represents the slope. Okay, let's put a picture with this to make sense of it even more. So we have our two endpoints. So our function is going to start somewhere at A. It's going to end somewhere over here at B. And we have a smooth curve that connects these 2 points together. So I'm just going to draw something like this. It may not look like this, but as long as it's continuous and differentiable, this theorem is going to work. So now we know there's going to be at least one number c in this interval for which the derivative at c is equal to the slope of the secant line that connects a and b. So in my picture, I'm going to label these points. So I'm going to label this first one as capital A. The x value is a, and the y value is f of a. And then my second point, I'll label this one as capital B, x value of b, and then the y value is f of b. Now if I connect these together with a segment, this is going to be the secant line between A and B. Now, what this theorem is telling us is that somewhere in between A and B, I should be able to find a point where the slope of the tangent line at that point is the same as the slope of this secant line here. So this line has a slope of f of b minus f of a all over b minus a. We should be able to find a point C where on my curve, the tangent line is going to have this same slope. So just kind of eyeballing this, maybe right about here, we have a point. So this x value is C, and there's going to be a tangent line that goes through that point that has the same slope as the secant line that connects A and B. So these two segments that I drew in, these should be parallel to each other because they have the same slope. So this theorem is an existence theorem. So what that means is as long as these conditions are met, this theorem is going to tell us that one of these points does exist. It doesn't necessarily tell us how to find this, but using some algebra, we should be able to apply this to a function and actually find that number c where this is going to happen. And that's actually what I'd like to do next. So my example says if f of x is equal to x minus 3 squared, there exists a number c in the interval from 3 to 5 that satisfies the mean value theorem. And we want to find that value of c. So the first thing we need to do is just verify that the mean value theorem is going to work on this. So we need to make sure that our function is continuous on this interval and that is differentiable on the interval. Now, the function I'm given is a polynomial. Polynomials are continuous and differentiable across the real numbers. So that means that the mean value theorem will work. So because we know the mean value theorem is going to work, we can conclude that there will be a number c such that f prime of c is going to be equal to f of b minus f of a all over b minus a. Now, the next thing we need is we're going to need to know f of b and f of a. So let's evaluate our function for our two endpoints. So we need to find f of 3, and we're also going to find f of 5. And we also want to find the derivative because we're going to plug in c to that. So we also want to find f prime of x. Let's go through and do all of this. So if I plug in 3, we have 3 minus 3 squared, which is 0 squared. So f of 3 is equal to 0. And let's also plug in 5. So 5 minus 3 squared is going to be 2 squared. So f of 5 is equal to 4. And then the last part here, let's find the derivative. So just using the power rule for functions, we'll bring the 2 down. And then we have x minus 3. We would subtract 1 from the exponent, but that would just be an exponent of 1. And using the chain rule, we would multiply by the derivative of the inside, but the derivative of the inside is just 1. And let's finish up by distributing the 2. So we get our derivative is equal to 2x minus 6. So now we have everything we need to find our value for c. So on the left-hand side of our equation, f prime of c, I'm just going to take the derivative and I'm going to substitute in c. So we have 2. Now instead of x, I'll substitute in c minus 6. And then on the other side of the equal sign, we can substitute something in for all 4 of these. So f of b, so that's my second endpoint, we figured that out was 4. F of a, that's my first endpoint, we have 0. And then in the denominator, the x value of that second endpoint was 5. And the x value of our first one is, we have minus 3. So to just do a little bit of simplifying here, we have 2c minus 6 is equal to 4 over 2, which is going to give me 2c minus 6 is equal to 2. Now, before we keep going, just taking a look at this right-hand side of the equation, it simplifies down to 2. So that means that the slope of this secant line between 3 and 5, the slope of that is equal to 2. The mean value theorem tells us that there's going to be another point c somewhere in between 3 and 5 that's going to have that same slope. The tangent line will also have a slope of 2. And that's what we're finding here. So if I add 6 to both sides, we get 2c is equal to 8. And dividing by 2, c is equal to 4. So that means that at this x value of 4, on this curve, the slope of the tangent line is also equal to 2, which happens to be the slope of the secant line between 3 and 5.